Today I want to do a bonus video on prime factorizations. We're not going to learn how to do prime factorizations, which we've done before. This is just going to be two problems to strengthen it and to see what we can do with them. Okay, so the first one many of you might have heard. Here's how the first question goes. I'm going to refer to this as the 100 doors question, and it goes as follows. There's 100 doors, and one person goes and swings open all the doors. Then the second person goes and flips the state of every door. So we're starting off with they were closed, closed, closed all the way down. After the first person, they're all open. After the second person, every other one got closed. The third person is going to go ahead and flip every third door. He's not opening or closing, he's flipping whatever the state of the third door, the sixth door, the ninth door, all the way up to the 99th door. The fourth person is going to do the same thing to every fourth door, and so on and so forth till we get to the 100th person. So 100 people are going to do this process. So after all 100 people have done this process, opening up every door number corresponding to that person's number, the question is, which doors stay open? So I encourage you guys to pause the video and think about it. And if you're thought about it and unpausing the video at this point, here's what this has to do with prime factorizations. Let's think about door number 1. Right, so door number 1, the only person that's ever going to touch it is person number 1. So door 1 will stay open. That's definitely correct. What other doors? Door number 2 will be opened and then closed by number. So number 1 will open door number 2 and number 2 will close door number 2. So 2 is not going to stay open. 3 will be opened by number 1 but closed by number 3. 4 will be opened by number 1, closed by number 2, and opened again by number 4. So far we have doors 1 and 4. Now you could do this until maybe you see a pattern, but let's think about this a little more intelligently. Let's look at a number like 36. 36 has factors that come in pairs. So you have 1 and 36, 2 and 18, 3 and 12, 4 and 9, and then 6 and 6. Now notice the 6 and 6. All the factors are different, right? 2 comes with an 18, 3 goes with 12 to multiply to 36, 4 and 9, but 6 goes with itself. What does this have to do with this problem? If you count up the number of factors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are not 10 different ones, but there's 9 because the 6 is repeated. So if you want a door to stay open, we want the number of factors to be odd. So it's like open, or open, closed, open. Or 5 would be open, closed, open, closed, open. So that way, any perfect square, and these are the first two, so 1, 4, 9, 16, 25, all the way down to 100, all of these have an odd number of factors. Because if you take the square root, it pairs up with itself. So for example, for 100, 10 pairs up with 10. So it only has one factor in terms of the square root. So 1 goes with 100, 2 goes with 50, 5 goes with 20, but 10 is a loner. So therefore this has an odd number of factors, and all of these have an odd number of factors. Every other number has an even number of factors because of this idea of factors usually coming in pairs. So therefore, which doors stay open? It's all of these doors, the perfect square number doors. Alright, so that's number 1, and that's an application of thinking about prime factorizations.